Hi, it's time for another math easy solution. Time to discuss further into polar coordinates, and now look at example 12 and then look at the question A of it, and basically revisit the Limaçons. Again, those were French for another word that means snail shell. And that was from example 11, so make sure to watch my earlier video on example 11. And this time we're going to go over an analytical proof, and it's going to be part 1 of it, which deals with part A, or question A. And in the next video I'll go over question B. So let's look at this. In example 11, the graph suggests that the Limaçon r equals 1 plus c sine theta has an inner loop when absolute value of c is greater than 1, and now we're asked to prove that this is true and find the values of theta that correspond to the inner loop. So what I've done is, I put a graph of the different types of curves for different c values that I graphed in example 11, so make sure to watch that. So here we have, recall r equals 1 plus c sine theta, and here's for all of them different values of c. We have negative numbers here, and what we're asked to see here is for just to consider absolute value of c is greater than 1. So here we have c is equal to 1, c is 0.7. Notice there's a sharp point here at c equals to 1, but then when c is greater than 1, in this case on the positive side, we end up having this loop right here. So notice there's a loop across there, and it goes around this way. So if you were to graph it, if you're rotating this way, you're going to have going all the way around, and then you go a loop this way, and then you come back down. I believe that's exactly how it looks like. And as you can see, there is a loop there. And also when you look at the negative side here, when you have negative 1, it's still that sharp point. All it is just flipped upside down. That's a sharp point. But here is when the absolute value of c is greater than 1. And this is, negative 2, absolute value is greater than 1. And as you can see, there's a loop across there. So very interesting as well. So there's a loop there. So now let's just look at the solution here. So to try to prove that we will get a loop for this case. So here's the solution. This is where I'll be writing it. So we have to notice, we see that the curve crosses itself at the origin, r equals 0. And as you can see, you could even see that here at the point here. That's when it crosses it. That's at the origin. And even on both these cases, c is greater than 0 here as well. And yes, we notice that, and in fact, the inner loop corresponds to negative r values. And to see that, let's look at this. What I'll do is draw a polar axis like that, where you have initially theta equals to 0, and then you rotate all the way across like that. But as you're rotating, what we end up having is a curve starting from here, goes up, goes here, and then goes down this way. And then notice what happens here. It's at the origin there. So it's at the origin there. And then it crosses the origin, goes around this way, and comes back there. And now we could see that it's negative, but first what I'll do is, for example, at this point here, so as you're rotating the angle, what I'm going to do is draw a straight line like that, so that we're rotating across this way. Then we get the angle. I'm going to call this theta 1. And then likewise here, I'm going to draw another angle, because as you rotate all the way across here and you go back to the origin again, we have another angle across here. I'm going to rotate that all the way across. This is going to be theta 2. So basically from this point all the way to this point, what this means is we have a range across here of where you're basically in between these angles. I'm going to write this theta 2 minus theta 1. This difference across, that is where the loop resides in between these two angles. And now if we had an angle in between, let's say somewhere across here, I'll draw this in blue. Notice here, so if we have an angle that rotates around like that up to this point, notice that there's no shape here, so then we need to go backwards. So we actually need to work backwards all the way across. So that means we have a negative r value there. So this is basically negative r values. And that's because we need to go backwards like that. And again, you can recall the definition of polar curves in my earlier videos where I showed that. Yeah, I showed that if you had, let's say, a polar angle like this, this is across there, and this is r theta, where you have this angle theta. The negative r of it, you just go to that angle and you just work backwards across, and this would be, at this point, this is just going to be negative r theta. So you just go backwards. And where the length to the origin O from both sides is going to be r and r. So yeah, the total length is r. Alright, so now that we got this all out of the way, we know that the curve crosses the origin r equals 0. So what I'll do is first solve the equation of the Limaçon for r equals 0. So we have r equals 1 plus c sine theta, and then set it equal to 0. So what we end up having is, we can move this over, we have c sine theta equals to negative 1. And then just divide the sine theta out, or then we have, actually divide the c out. So we have sine theta equals to, just so we get the angles, negative 1 over c. And again, we should have two angles in between here and negative r values. So now let's first consider the following cases for the values of c and how the curve of the Limaçons are shaped. And what I'll do is I'm just going to draw a line like this, just a horizontal line indicating the values of c. So we have, let's say, zeros over here. We won't look at that in particular, but let's say we have a point here. This is going to be 1, and here we have negative 1 across. So what I'll look at is negative 1 and 1, as well as from this side. So we have c is less than negative 1, and let's look at in between here where c is less than absolute value of absolute value of c is less than 1, so in between here is just a fraction. And then also we'll look at to the right side here, where the right side here c is greater than 1. So first let's check c equals plus or minus 1, so these points right across here and here. Alright, I'll just uncircle that. So if c is equal to plus or minus 1, what we end up having is c equals to, or not c, we'll write r equals to 1 plus c sine theta. And again, that's just the equation of the Limaçon. And now we have c is plus or minus 1. So what this means is that this equals to plus or minus, and then that's just 1. And now we write plus or minus sine theta. So it could be plus or minus sine theta, but what we do is, well, recall the equation of a sine curve like this. If this is theta and this is sine theta, like that on the xy axis, if you just graph a sine curve, it looks something like this. Draw this a bit better, etc., where the absolute max here is 1. As you can see, this is just 1, and then it goes to the bottom lowest point is just, well, these are all, put this a bit higher. Put that above there, and this is at negative 1. So what we have is basically the absolute value of sine theta is going to be less than 1, or less than or equal to 1. So it can't be greater than 1 like that. So thus what we end up having is, we'll write sine theta. Sine theta is less than or equal to 1, but greater than or equal to negative 1. And what this would mean is if we had 1 plus or minus, I'll just write r, so thus r equals 1 plus or minus sine theta. Now this is going to be a maximum if it's just the maximum of sine there, and we have a plus. 1 plus 1 is 2. And then, or it's going to be greater than or equal to the lowest part, which is when this is negative 1 and we have a positive. So 1 plus negative 1, because if we do 1 minus negative 1, 1 minus negative 1, the negatives cancel, we just get a 2. So now we have, this one's going to be, well, 0. The lowest we could have is just a plus and a -1, or a negative here and a +1 there. So 1 minus 1 is 0. And we could write this on the other side. Let's circle all of this. And then on the other side, again, that's just 1 plus 1, or here equals to 1 minus 1. So what we end up having is, well, r is greater than or equal to 0. So this means it's not negative. And that's why we have the sharp point at r equals plus or minus 1. And in fact, I've already gone over this in my earlier videos. It's just a cardioid or a heart shape like that. So it goes right on it. There's no negative values there. Yeah, so thus, since r is not negative for c equals plus or minus 1, we don't get a loop. And in fact, it's just a cardioid, as I've gone over in my earlier videos and examples. So check those out. Yeah, so now let's check if absolute value of c is less than 1, then this equation has no solution and there is no inner loop, and I'll explain why it has no solution. So we're looking at this inner one right there, and the reason is because when r equals to 0, we have that same equation here. Sine theta equals -1 over c, and this is we have sine theta equals -1 over c at r equals to 0. Now the only problem with this is if we have absolute value of c is going to be less than 1, then what we end up having is then absolute value of -1 over c. This is greater than 1, and that's because you have a fraction like there. For example, i.e. if you have c equals to, let's say, c equals to 0.5, then what we end up having is -1 over, or just not even use the absolute value sign. Let's just say then if we have c is equal to 0.5, then we have -1 over 0.5. The same thing as writing 1 over 2 here. The 2 flips above, then we get is, well, -2 right there. But this absolute value, the absolute value is greater than 1 there. But notice here, this is between these right there, between 1 there. So we can't get a -2 for sine. Yeah, so we write but, or right, capitalize. Yeah, but we have absolute value of sine theta. This is less than or equal to 1. Yeah, so what we have is, well, this for c is less than 1. This is hashtag not possible, like that. So now let's look at the next case. If c is greater than 1, and that's on the right side there. Where did I just skip that? So on this side here, c is greater than 1, and what we should have is this loop like this there, where it's on the positive, or on the upside of the horizontal axis, on the vertical side of it. Yeah, so if c is greater than 1, then on the interval 0 to 2 pi, again, if you rotate all the way across, I'm just going to look at all the way across to 0, theta equals to 2 pi. So you do a full rotation and go all the way over there, like that. Yeah, then on this interval, the equation has 2 solutions, and I'll show that. So again, at r equals to 0, we have sine theta equals to -1 over c. Now this is less than 1 when c is greater than 1. And again, i.e., for example, if you had c equals to, let's say, 2, because it's greater than 1, yeah, then what we end up having is a -1 over 2. Well, yeah, this just equals to, well, -0.5, like that. And then basically you are -0.5. Well, that's obviously less than 1, and even the absolute value of it is less than 1. It's just a fraction there. So thus sine theta, which equals to -1 over c, well, this exists, and then we have a solution to it. So let's write this exists. And in fact, on this interval 0 to 2 pi, we do have 2 solutions, and we can see that right here. So first, what I'm going to do is, if you have your axis vertical and horizontal like that, I'm just going to draw these in 4 quadrants. For example, for the ratio 1 over c, what I'm going to look at first is the positive side, and the positive side is over here, I'm going to draw an angle. I'm going to write this as alpha. Actually, this one's gamma, not alpha. So I'll just draw gamma like that, just Greek letter. And then what we have now, the ratio, I'm going to write this as opposite over hypotenuse as c. Yeah, so we have this ratio across there where we have sine alpha equals 2, and this is on the first quadrant. Here 1, 2, and then we have the 3, 4 quadrant. And now sine theta number is just opposite over hypotenuse by definition, 1 over c. And if we were to solve for the angle, we have this angle gamma equals 2, and this is using the inverse sine, and then we have 1 over c. So that's just definition. You can just find it using the inverse, so that's the angle there. And I'm going to circle this because we will use it. Yeah, so but that's for positive 1 over c, but the issue here, c is positive, so we're going to have a negative ratio, negative 1 over c. Hypotenuse is always positive, so what we end up having is the opposite needs to be negative. And you could see that ratio if we just draw this exactly across here. This angle is just by symmetry exactly gamma. Now we have a negative 1, so that's a positive 1 there. We have a negative 1, we have c, and now this ratio here is the negative 1 over c. So but then to get that exact angle, we got to rotate it from here to here. Or before even that, I'm just going to erase this and first draw out this difference. This one is just pi. That's just 180 degrees, just a straight line by symmetry. So that's just pi. So now what I'll do is I'm going to draw this all the way across there. Yeah, actually, to make it easier to see, I'm just going to erase that. And we already know that this is just 180 degrees from here to here, and then we just add this alpha there by symmetry. So we have this angle across. I'm going to call this angle right here as theta 1, and this equals 2. Yeah, this just equals to pi plus this gamma. And now we can also get another negative 1 over c by just flipping it over here, like this. And so if this angle across here is going to be gamma, that's just a mirror image. This is negative 1, we have a c, and then we could rotate this all the way from here to here. And now this angle, I'm just going to move this around, this is the fourth quadrant. Now this angle across, that could be considered as the full angle 2 pi minus this gamma. So yeah, we have, I'm going to call this angle 2, and this equals to 2 pi minus gamma. Move this 4 there. Yeah, so thus we have these two solutions. So thus we have two solutions because two solutions in the interval 0 to 2 pi, like that. And these are the two ratios there for the angle theta 2 and theta 1. So what we end up having is theta 1 is equal to, that's just pi plus gamma, where we know gamma is just using the inverse of sine, equals, well, this is going to be pi plus inverse sine of negative 1 over c. Actually, there's no negative there because we're using this gamma there. So that's just going to be 1 over c, like that. And then the second one, theta 2 is equal to 2 pi minus gamma, which is equals to 2 pi minus inverse sine of 1 over c, like that. And we could just circle this whole thing. Yeah, so now we have these two solutions, but now we need to check if they're negative. And what we could do is, well, note when you look at the angle sine, well, not the inverse, just the sine theta, the function sine theta. So what I'll do is write this like this for the y-axis is sine theta. I'm going to draw this around up to 2 pi, and this is our theta. This is 2 pi there, and this is across here is pi, and between here is our pi over 2, not negative, just pi over 2. And then remember, in between across here, this is just 3 pi over 2. Yeah, so what we have now is these angles here, angle theta 1 and theta 2, where we're adding this gamma. So if we have theta here, And now this is, remember, this is just a sine function. This is positive there. And then we have at the bottom here, this is all negative there. So gamma is going to be, well, theta 1 is going to be pi plus gamma. So it should be somewhere here. This is going to be theta 1, where the distance between these two pi and theta 1 is gamma. And then on the fourth quadrant, remember that's the third quadrant, now it's the fourth one in between here. So that's 2 pi. So we need to have theta 2 somewhere over here. And now the difference across there is gamma. That's just 2 pi minus gamma, like that. So we get that. But notice what happens across here. If we find the values of sine, we get these two values. These are actually identical values of sine here. But now if you notice what's in between, we have this is higher in between the angles. If you go to the right of them, it goes down, and then added, it's these two values. But above it, we have in between this range, like that. This is, well, it could be seen as, well, quote, more negative. So this is more negative than the other sides, or even at the angles, theta 1 or theta 2. So more negative between theta is between theta 2 and between theta 1. Yes, so now because it's more negative, what we also notice is that since r is continuous, that's just because it's just a 1 plus c times sine theta. Sine theta is obviously continuous function, and we're just adding 1 and multiplying it by another constant. There's no jumps in it. So it's continuous for all values of theta, and r of theta 1 equals r theta 2, which is equal to 0. Because remember, these are the points where we found when r is equal to 0. We must have that r is less than 0 because the absolute value of sine is larger between theta 1 and theta 2 than at theta 1 and theta 2, because between it is more negative. For example, let's just write this out to make it a bit more sense. So we know that r equals 1 plus c sine theta, but remember, c is always positive, in our case greater than 1. So now we have 1 plus, actually instead of plus, I'm going to write this as, I'm going to take this as a negative, because remember, this is negative for the whole side, for the whole thing between pi and 2 pi. Yeah, so I'm going to write this as negative c absolute value of sine theta, like that, for, and I'll write this as pi 2 pi, like that. Yeah, so between that range there, we'll just equal, yeah, it's all negative, so then we could just put the negative there and use absolute value there. So, and we also know that r of theta 1 equals to r theta 1 equals to r theta 2, which equals to 0. Yeah, so that's equal to 0. So, and we also know that, and I'm going to write now the absolute value of sine, yes, sine theta 1, yeah, this equals to absolute value of sine theta 2, and you could see that here. It's just perfectly symmetric there. It has the same exact ratio, because remember, trigonometry is just the ratios you're dealing with. So these are exactly in line, but then the absolute value is less than in between here. Yeah, so this means that this is less than, actually no, the sign is less than, but the absolute value is, actually I got that wrong. Yeah, so this is less than sine theta, for theta is between theta 2 and theta 1, like that. Yeah, less than the absolute value of it. Yeah, that's what I meant. So less than absolute value. So if it's less than absolute value, this means that between is larger or more negative, and we know that we're going from 0 here, and everything is just continuous. So if r theta 1 equals r theta 2 equals 0, but now we're subtracting by an even larger number, then it has to be negative. Yeah, so thus r is less than 0. And again, for theta is less than theta 2, greater than theta 1. Yeah, so that's what we have is for c is greater than 1, we have two angles in which r equals to 0, that's theta 1 and theta 2, and between them r is less than 0, and thus we have a loop. It's just negative numbers there. So thus we have a loop, and you could see this again visually if you draw polar axis like this. So what we have is, here's that curve. Let's draw that again. So something like this, and then it goes over here. Now we have it 0 at this angle across there. And I'm going to call this theta 1, and that's in the third quadrant. And then in the fourth quadrant, we have negative values across there, and then we loop all the way across until we get to this angle. So in between we have negative angles. So this is going to be our theta 2. And then once we come back, we have starting to have positive values of r. And again, if you had an angle in between somewhere across there, so then we rotate across, there's the angle, we'll call this phi, or actually write this as phi, and then basically you got to go backwards. Yeah, just erase that angle there. So we have to go backwards across, and then we have a negative r there. And this happens for all values in between here, hence getting that loop. So if you have an angle there, we get all the way across there, and another negative r across there. And again, this is in between these two angles. This is theta between theta 2 and theta 1. Yeah, so now that we've proved that for c is greater than 1, and now similarly for c is less than -1, where the absolute value is again greater than c, greater than 1, the absolute value. Yeah, we could do pretty much the exact same thing, just in like opposite form, then we get that symmetry across, but I'll just do it for completeness sake. So the solutions are, we have, well, a number at r equals to 0, we have sine theta equals to -1 over c. But now notice this is negative c, then we have a negative there, negatives cancel, this equals to, well, positive 1 over absolute value of c. And again, this is because because c is less than 0, it's a negative, so we have a negative on top divided by a negative, negatives cancel, equals to a positive. And now we already know that the solutions exist because this is greater than 1. We have a fraction where the overall one that is going to be, well, less than 1, so solutions exist like that because it's a fraction below 1. Yes, if it equals 1, that exists as well, as I showed in the cardioid one above, but we're dealing with less than 1 here, so its solutions exist. Okay, so we need to look for the ratio 1 over c, so we'll draw the quadrants again here. And notice this time, this is the first quadrant, this is the second, this is the third. So when we deal with ratios for our angles, notice this one, I'm just going to draw this like this. This is 1, and then this is the absolute value of c because the number has to be positive. This is just... yeah, this is just our theta there. We don't need to use the gamma. So we just write theta, and I'm just going to write this as theta 1. Or actually, just for consistency's sake, I'll just write this as gamma. And now this is actually just the same as theta 1. So gamma equals to theta 1 because the ratio is the same. And again, we have sine of gamma equals to 1 over absolute value of c, which is just, well, negative 1 over c. So we have the negative because it's still positive since c is negative. Finding gamma like this equals 2, and now we have inverse sine of -1 over c like that. So that's our gamma. Same thing as theta 1. Now if we want to get another positive one, we can't go to the bottom because then we'll have a -1 over absolute value of c. We just go on the second quadrant. So we just go across there like that. This is right angle. This is going to be 1, and then another absolute value of c, where this distance across is again gamma. And now from here to here, this is just going to be theta 2, which equals to pi, the horizontal full angle, 180 degrees. So pi minus gamma, like that. Yeah, so thus we have two solutions. Let's write this quadrant above there, and this one here. So thus we have two solutions, and in these solutions we have theta 1 equals 2, that's just gamma, that just equals to gamma like that, and that equals to inverse sine negative 1 over c, like that. And likewise, write this a bit neater, like that. And then gamma 2 equals 2. This is just going to be pi minus gamma, which equals to pi minus, and then gamma is just inverse sine of negative 1 over c, like that. And then we could just circle these like that. And now the next step is, like before, we want to find out if r is negative. So we have two solutions. Now we need to check what the r values are. And again, note here we'll draw the same sign like this. So theta, this is sine theta on an xy axis. And I'm going to draw this across like that, again up to 2 pi. So notice here, this is up to pi. We're going to be dealing with from in the first two quadrants, because if you go to the bottom we have a negative ratio, so we're only dealing with the positive ones between 0 and 2 pi. So we're looking at in between here. So then if this is going to be our pi over 2, now the first one is just gamma's alpha, where alpha is between 0 and pi over 2, so we're just somewhere over here. This one is going to be this is just this is just 5. I mean, not 5, I mean, this is theta 1, yeah, I said brain fart or something. Yeah, so that's theta 1, and now on the flip side is somewhere over here, where again, this difference is just gamma, and likewise, exactly symmetric across here. Let's draw this better. Yeah, like that. Just going to curve it. Yeah, so it's not drawn to scale, but that's theta 2, and now across this difference is, again, that's going to be gamma, like that. Like this is gamma. And now again, notice that this is all positive. So this whole thing is positive here, but notice that the above this, in between here, yeah, so if we look at the angle in between across these two angles there, this is from theta is less than theta 2, greater than theta 1, and move this above. What we get is, well, we have more positive in between here. So more, or just larger, more positive, absolute value is larger, i.e. just larger number of sine. So i.e. larger sine theta. Yeah, so now also similarly, since r is continuous for all values of theta, and r theta 1 equals r theta 2, we must have r's less than 0 or negative, because sine theta is larger between theta and theta 2, theta 1 and theta 2, than at theta 1 and theta 2. And again, just like above, r equals 1 plus c sine theta. But now we have sine is negative, and it's greater than 1, so we have 1 minus, I'm going to look at the absolute value of sine there, sine theta, because remember theta is positive, this is 4, and I'll look at the range from 0 to pi, like that. Yeah, so because above here is all positive, but then the c is negative, we're going to be subtracting from positive times negative, we have a negative like that. And we also have r theta 1 equals r theta 2 as we solved it above there. This equals to 0. And we know, yeah, and basically we know that the, or just sine theta, we don't have to use absolute value. Sine theta 1 equals sine theta 2. They have the same ratio, 1 over absolute value of c, or negative 1 over c. Which becomes positive because negative is positive. So this equals to this one, and this is less than sine theta for theta is between, theta is between, I'll write it like this, theta less than pi over 2, greater than pi over 1. So in other words, this sign is more positive there. So again, you're subtracting from a larger number, where the original one here, r is equal to 0. So now you're subtracting something greater and it's continuous, so it has to go to negative. Yeah, so we have is thus r is less than 0 for, again, theta 1 less than theta, and here for theta 2. So for theta is less than, in between those, so we'll just circle this r is less than 0. Yeah, so basically thus for c is less than -1, we have two angles in which r equals to 0, and between them r is less than 0 or it's negative, thus we have a loop, and very similar to this right here, but now we're flipping it. So if you go all the way across to see how it looks like over here. So, and there's our two angles. Now it's on the first and second quadrant there, but then we need to, for anywhere in between, like here, we need to look at a negative r, and likewise here, negative r, etc. And these are in between. This is the quadrant here. I'm going to write this quadrant 1, quadrant 2, and these are our angles theta 1 and theta 2. So yeah, there's the other quadrant. Now you're going backwards. There's a loop at the bottom, and the last part of this very extensive video proof. Thus, for absolute value of c is greater than 1, the Limaçon has a loop, because I proved it for both of these sides. Yeah, for c is less than -1 and c is greater than +1. The curves for positive and negative values of c are mirrored about the horizontal axis, as I showed above. And this is because, well, if you look at this case, 1 plus c sine theta equals to 1 plus or minus. And now what we're going to do is look at plus or minus c, the absolute value of c times it by sine theta. And where sine theta is by definition, just again, as I've drawn it many times, here's sine theta like this. It just goes up and down. So we have a positive, negative. So based on whatever the value of c is, all you're going to be doing is flipping. Yeah, flipping the direction where r goes. And then again, remember this is sine theta. Absolute value is less than or equal to 1. So all you're going to be doing is going from 2 to 0, and then even less than that. Actually, it's based on the value of c right there. So basically, all you're doing, the only difference is plus and minus here, and then the only difference is a plus or minus. So you're obviously going to be mirroring from the top or bottom like that as the r value changes. So anyways, that's all for today, and again, just to show you that visually here. So notice here for negative we have this one. All it is just flipped across. This vertical top there, then we get flipped, because again, because all we're dealing with is a sine function where it goes up and down, exactly mirrored. Anyways, that's all for today. Hope you learned from this very extensive proof video, and in part B or part 2 I'll go over question B, which I believe might be slightly simpler. I'll have to double check. Anyways, that's all for today. Hope you learned. Like always, you can download these exact notes in the link below, and also view it on steemit.com. Follow me at MES. I'll upload this shortly after I upload this video. Anyways, thanks for watching, and stay tuned for another Math Easy solution.